So we're all about right now estimating parameters. That's all we're doing right now. That's what the first bit of the course is all about. Take a study, collect some data, crunch the data, and try to get bounds on whatever you're trying to study, get bounds on what it is. So right now we have two parameters we're going to estimate, P and mu. Population proportion, population average. Okay? The center of the data set that we collect for discrete data, we term it P hat. The center of the data set that we're collecting for average data. I notice I said average and not continuous. It's usually continuous because it's a measurement, but you can also average discrete data, and you'll see why momentarily. You'll see why momentarily. But that average, we're going to call X bar. The margin of error. Now, write this down only if you're really, truly interested. And we're going to come back to it. The margin of error for this bad boy is a formula you will never calculate manually. I know. I know. As soon as I start drawing formulas, it starts to yawn. It's almost inevitable. It's like a nap time. There's a formula. Oh my God! I can't keep my eyes open. What is this guy going to be? What is that guy going to be? What do you remember from 243?
Sigma over the square root n.
Nice, very nice. Except I'm not going to call it sigma, Will. I love that. Thank you. Because sigma is who? Of the what?
Population.
Yes, it's the population standard deviation. Who did we use? Who did we use in 243? We didn't use sigma. Your TI gave you both, which I can't stand. And there was a sigma, but right above him in the sample one, little s. He's the guy we're going to use. He's the guy we're going to use, little s, and then over root n. But that's not entirely complete yet. In much the same way, this wasn't complete. Remember how this guy, we called that a standard error. Michael, you actually called it a standard error. And then I said as soon as you multiply that standard error by this multiplier of a critical value, which we're calling z in that case, as soon as we multiply it by that, we create a margin of error. That's the definition. And usually that z is a 2. Usually that z is a 2. And as soon as you have that bad boy, you've set up this. You've set up a p hat minus the margin of error and a p hat plus the margin of error. And you see what I've done there? I've taken that sample statistic and added and subtracted the margin of error from it. And the hope, with 95% confidence, as Mindy pointed out before, is that wherever we're looking for, in this case the population proportion, is wedged in between those two numerical values. Now that might seem a little weird because it looks mathy, it looks symbolic. It looks symbolic. But if you think about it, this is what your TI gives you. Your TI gives you these two numbers. When you run one prop z int, it comes back with a set of parentheses and then a number, comma, a number. The smaller number is this one. The larger number is that one. And all we know with a set level of confidence is that what we're looking for is between those with 95% confidence.
And that's what the confidence interval is.
That's what a confidence interval is, Rosie. You got it. That's what the confidence interval is. What we need is something similar over here that catches mu between x bar plus the margin of error and x bar minus the margin of error. And we're almost there. We're damn close. Will, this is perfect in central limit theorem. And I made sure in 243, you don't remember this because it's been 3 months if you had me, I made sure to start calling that standard error back then. Because this is standard deviation. Just like that times n is standard deviation of the binomial. But as soon as you adjust it for inferential purposes, that's where the root n comes from, and the root n over here comes from. But the trick is, what goes there? What goes right there?
Critical value.
The critical value. Now this critical value is very, very important to us. It's very, very important because it comes to us from beer.